Hello, everybody. Welcome back to Math Counts Hour. We are going to work problems today from the 2009 State Math Counts Sprint Round. And here we go. We're going to take a look at some of these problems. I think with you, young sir, I'm going to skip the first page here and let's find some good problems to work on page 2. How about we start with number 7?
Okay. Hi.
5 termites are eating through a piece of wood, all beginning at the same edge and going in the same direction. Woody is 20 millimeters ahead of Muncher. Cruncher is 10 millimeters behind Woody. Muncher is 5 millimeters behind Nibbler, and Biter is 15 millimeters ahead of Cruncher. How many millimeters is the distance between the 2 termites who are farthest apart? It's a lot of words going on. What can we do with this one?
Draw it out.
Draw it out, okay. Like a line segment?
20, yeah, I think it's 25.
I think it's 25? I think it's 25 too, but what'd you do?
Started placing the termites.
So Woody, then Muncher, and that's 20. Then what do I do?
And then you Cruncher. Oh, halfway. And Muncher. And then we place Nibbler.
Where's Nibbler?
It's 5 cm in front of Muncher.
Okay, and finally?
Biter is 15 ahead of Cruncher.
So where does that put Biter?
25 away from Woody.
25 away from Woody?
Yes.
I thought Woody was out in front.
Oh. Oh, it's 5 ahead of Woody.
Okay, yeah, 25 ahead of Cruncher. Who's a Biter? Okay, and so in total, actually maybe the easiest thing is to say, hey, Muncher and Cruncher are 10 apart, and Cruncher and Biter are 15 apart here. Okay, so I agree with your answer. Good. Okay, why don't you pick the next one? Don't look too long.
11.
11, okay. Why do you like 11?
Just saw the word test. Don't know why. Just picked up a random one.
Good. Okay, here we go. 30 students took a test on which it was possible to earn only integer scores ranging from 3 to 10 inclusive. If exactly 24 students passed by earning a score of 7 or higher, what is the highest possible average of the 30 scores? What do we do with that?
24 students got 10, and the remaining 6 got 6.
Yeah, we're trying to find the maximum, so we might as well maximize everyone that we can. Put 24 students right there at scores of 10, and then everybody else. What'd you say?
Everybody else gets a 6.
I agree. Since we can only get integer scores, so we have 6 6s. So now what?
We sum it up and divide it by 30.
How do we sum this up?
6 times 6 plus 24 times 10.
Okay.
I got 9.2.
Okay. I'm going to show this. I would like to do a little canceling. We can bring out a factor of 6 in the numerator and denominator, and that gives us 46 over 5, which is that what you said, 9.2?
Yeah.
Okay, just to be sure we didn't do our arithmetic wrong, I checked, and we are correct. Good. All right, let's find another.
Number 16.
Number 16. CAC6. Okay. A rectangular garden has a length that is twice its width. The dimensions are increased so that the perimeter is doubled, and the new shape is a square with an area of 3,600 square feet. What was the area of the original garden in square feet? What would you like to do with this one?
Find and assume a variable and solve.
Possibly. X by 2x. Which has an area of 2x squared.
You want a square. The total perimeter is 6x. Oh, you add 2x and 1x to the sides. So it's 3x by 3x. Which is 9. So x is 400. No. 2 is 20.
So x is 20?
Yeah.
I agree. So what's our answer?
800.
I agree. So I'm going to go ahead and mention I had a different instinct for how to begin than you did. There's nothing wrong with what you did. It was pretty straightforward and nice. One thought that I had was to work backward with a problem like this. Why is it, a lot of geometry problems are, it's good for us to work backward, or word problems, and this is both. What advantage do we have working backward?
You can already find the dimension of the square.
We can already define the dimension of the square. We can quickly say that the perimeter is 240, so the perimeter of the original was 120. And then we say, hey, we've got 2 by 1, and we're taking 60 and dividing that into 2-to-1 ratio, and we can pretty much use our number sense there, and then multiply those two numbers to get our same answer of 800. And we never even used a variable. That's one of the, sometimes when we work backward, we find enough information that we can simplify what it is we're doing. Okay. I'll pick, let's do number 17.
Okay.
So what do you think, Aaron?
There's a relation between 2x and 2y, I think.
2 to the x and 2 to the y, or 2x and 2y?
Oh, 2 to the x and 2 to the y.
Their difference is 8. And it's important to note that x and y are integers. Do you know what type of equation this is, where we have variables that, where the domain of those variables is integers?
I don't think I remember the name.
It's a Diophantine equation.
Oh, Diophantine.
And here, those variables are in the exponents, which is a little bit weird, but I'll go ahead and mention one of my favorite tactics with Diophantine equations is to factor anything that I can. And, or I like to say factoring is factoring. And so I'll factor one side if there's just a constant. I might isolate the constant and write it in terms of its prime factorization. Now, I bet a lot of students just try to use number sense on this. I bet a lot of people.
Oh, I see the answer now.
What's the answer?
X equals 4, Y equals 3.
That's correct. And how'd you see it?
Usually when it's like 2 to the 5 or something minus 2 to the power underneath it, it's just the power underneath it.
Right, because we're doubling each time.
Yeah.
So that's a good number sense explanation. If you see one like this that is too hard to apply number sense to, here's a possibility. Factor out 2 to the y and multiply that now by 2 to the x minus y minus 1. And that's equal to 2 to the third. Now x is greater than y, so 2 to the x minus y is even, meaning that this right here is odd. If that's an odd integer that is a divisor of 8, what do we know about it?
Then 2 to the x minus y minus 1 should be a power of 2.
It's an odd power of 2. How many odd powers of 2 are there?
1.
Yeah, just
Is it
one.
0?
Not 0.
Wait. 1.
1. Yes, that factor must equal 1. And so if it must equal 1, then the other factor must be 8. Y is 3. And then we come back here and go, well, x minus y was 1, so x is 4. But really and truly, I bet most students just do this by number sense. Sometimes we can, sometimes we can't, but it's good to know what tools are available when we can't. Okay. You pick one this time.
Hmm. 20.
Let's see. 24 4-inch wide square posts are evenly spaced with 5 feet in between them to enclose a square field. Okay.
Hmm. $58.
It's going to be greater than that. Let's talk about a side.
Oh, I thought I got each side is 58.
Oh, each side is 58?
Yeah.
That's
So
not right either. How many posts are there per side?
7.
Okay, I agree with that. Okay, so we're on the same page there.
So there's 6 5 feet in between.
I agree with that.
And there are 7 4-inch wide posts. So it's 5 times 6 plus 7 times 4.
Be careful. Read the problem carefully.
Oh. So that's 7/3 of a feet.
Right. And then that is what we want to multiply by 4.
I got 129 1/3, I think.
That is correct. Let's talk about computation for a second. I actually decided not to combine the terms inside because that number was so nice and easy and round. And then when I multiply 4 times 7 times 1/3, I've got 28/3, which is 9 1/3, since we're going to express this as a mixed number. What did you learn from that problem?
Read a little more careful sometimes.
Yeah, and of course you've heard that before, and we've all made that mistake numerous times before. So it's definitely one to be a primary focus of your procedural practice. But let's move on. I will pick one. You know what? I'm just going to go straight down at this point. What do we do to find solutions to a polynomial, roots of a polynomial, or solutions to a polynomial equation?
You try to factor 225 into two numbers that could sum up to 34.
Well, in general, we try to factor. Now, the higher degree the polynomial, the harder that is. I'm going to make this a little bit easier.
Complete the square?
Perhaps. If we substitute y equals x squared and y squared for x to the 4th, our equation becomes y squared minus 34y plus 225 equals 0. Is that easier to deal with?
Yes.
Yeah. Now we can do any number of things. We can complete the square. We can apply the quadratic formula. We can factor. Is this one that you can factor nicely?
Yes, I got y minus 17 squared equals 64.
So you completed the square. Okay. You're completing the square, and you add 64 to both sides. And that gives you on the left-hand side y minus 17 squared is 64. Now what?
Take the square root of both sides. The smallest would be 11. Wait, oh, 9.
Well, be careful.
The answer was it's asking for the smaller solution, so it would be 9.
The smallest solution of what equation?
Of x to the 4 minus 34x squared plus 225.
Right. Anytime you make a substitution like this,
Oh.
you need to remember to think to substitute back. And this
So,
is, go ahead.
So it would be 3 and 5, not 9 and 25.
It's not 3 and 5.
Positive 3, negative 3, positive 5, negative 5.
Right. So what's our answer?
Negative 5.
Negative 5 is the correct answer. So let's talk about a few things. One is to get used to just every time you, really and truly, I think it's probably good to reread every problem before you put down an answer. At least reread the question part, but this problem is short enough to read anyway, right? So just reread the problem. Another thing too is, know and make use of all of the properties of any of the mathematical objects you're dealing with or mathematical statements. How many solutions are there to a fourth degree polynomial?
4.
4. Some of them may be non-distinct. You may have double roots or triple roots or something like that. But in general, there are 4 roots to a fourth degree polynomial. There are n roots to an nth degree polynomial. That's fundamental theorem of algebra stuff. So if you wind up with 2 solutions, that should be something where your number sense or your math sense kicks in and tells you, oh, wait, I forgot to do something. So it's another reminder to go back and plug back in your original variable. But I want to point out that this right here is something that we should be able to factor fairly easily. And let's talk about the number sense approach to factoring. 225, the only primes that divide that are 3 and 5. Is 34 divisible by either 3 or 5?
No.
No. So if it does factor nicely, we need both powers of 3 in one of the roots and both powers of 5 in the other one of the roots. And so 9 and 25 are pretty natural to check, and they do add up to 34. So y minus 9 times y minus 25. And as you get the hang of that, students who have been doing algebra for a number of years, they see this rather quickly and just factor that right away and then jump straight to the roots. Now there are fewer places to make a mistake.
Yeah.
Okay, let's continue on with problem number 22. Two arithmetic progressions that have some common values. What is the largest value less than 500 that they have in common? Here's a question. What do we know about the relationship between any two terms in the first sequence?
You add a multiple of 3.
Okay, so their difference is a multiple of 3. 3 divides the difference between any two numbers in that sequence. Well, what do we know about any two numbers in the second sequence?
Difference of 7.
Their difference is necessarily a multiple of 7 because that is their common difference. Okay. Suppose there is some future number in this first sequence, I'll call it n, that is also in the second sequence, given that we've identified that 17 is in both sequences, right?
So you want two numbers that, a number that is 2 more than a multiple of 3 and 3 more than a multiple of 7.
That's one way to look at it. We could solve that way. But think about this, the difference between, so n and 17 are two numbers that are in both sequences. We know that the difference between any two numbers in the first sequence is 3, and the difference between is a multiple of 3, and the difference between any two numbers in the second sequence is a multiple of 7. So if n and 17 are in both sequences, what do we know about n? Or what do we know about n and 17? Their difference, their distance apart,
is a multiple of 3.
It's a multiple of 3 and
7.
And it's a multiple of 7. Therefore,
it should be a multiple of 21.
yes.
Oh, and then you just find a multiple of 21 and try to get it as close as possible to 500.
Very good. Yeah. N minus 17 equals the least common multiple of 3 and 7 times some variable, some integer, m. So n can be any integer, as it turns out, that is 17 more than a multiple of 21. And now we want that to be less than 500. So let's solve that inequality.
500 actually works, I think.
Does it really?
Yeah.
Well,
it says
it is less than 500.
So it should be 579.
So we plug in 22. We get 21 times 22 plus 17. What did you say your answer was?
579.
Close.
Wait, no, 479.
479, right. Yeah, and you probably did it the quicker way, just subtracting 21 since you noticed that 500 was right on the dot. So you had to go before that, and that's a good, clever way to do it also. But we could also plug in m equals 22 and just say 21 times 22 plus 17. Good. Do you like this spacing method?
Yeah.
I think it can make for quick work for of some of these. Okay. Problem 23. an isosceles right triangle is removed from each corner of a square piece of paper to create a rectangle. AB is 12. What is the combined area of the 4 removed triangles? Pardon me, I have the hiccups right now.
Mm-hmm. I got AB is 36.
Is that what we want?
We want the area of the removed triangles.
Mm-hmm. Is that how you got started?
Yeah.
Well, let's see. We want the combined area of the 4 removed triangles. What is that area?
A squared plus B squared.
Right. We can shove those isosceles triangles together to make 2 squares with sides A and B.
So 144.
And their combined area is?
144.
Not 144.
Wait. 72.
72, right. Yeah, a lot of times we don't have to or we can't specifically isolate exact values for the variables, but it doesn't matter because we just relate what we can find to the expression of the quantity that we're looking for. Okay, let's take a look at problem number 24. Huh.
Simplify it.
It's tough to simplify the square root of a plus root b without knowing what the values are. Sometimes it can't even be simplified. But I did some playing around. What did I do here?
You squared everything and moved it over, kind of.
That's true. Even before that, though, what did I do there?
Assume a variable. for an integer.
Yeah, I named the expression that we were focused on. I named the beast, gave the variable name, and then I squared both sides. Why did I do that?
To get rid of the first square root.
Yeah, yeah. And we're dealing with integers, right? Everything's an integer.
So b has to be a square.
Yes, exactly. The left-hand side of this equation is an integer, and the right-hand side must be equal to it, meaning that the square root of b is an integer. That's how we write that. So b must be a perfect square. Okay? So b is a perfect square.
6 of them.
There are 6 of them, exactly. Square root of b can be 1, 2, 3, 4, 5, or 6. Now what?
They all could work.
What are we trying to do?
You could just test every integer for a,
Sure.
because there are only 10 and it's not that many.
Yeah, we want to create perfect squares. We want to count the number of ways that we can do that. Ordered pairs A and B. And A is 1 to 10. So we're adding 1 to 10 to 1 to 6, forming squares. There are different ways we can go about this. If you want, you can just test them all.
I think there's
60.
one. All of them work, but 9.
What do you mean all of them work?
All of the numbers between 1 and 10 work for a, except for 9, I think.
Is that what we're trying to count, the number of values of A that work?
The number of ordered pairs.
The number of ordered pairs. Why is that important?
You can repeat a twice.
We may have values of A that work more than one time.
Yeah.
Okay.
Ten ordered pairs?
Good, that's right. How'd you do that?
Kind of just tested all the values, but most of them only have one possible one.
Most of them only have one. I think there's just one with 2.
Yeah.
But here's something we could do to be a little quicker. The sum is at least 2 and no greater than 16. So the only possible squares are 4, 9, and 16. We can count the ways to do that. With 4, we've got 1, 3, 2, 2, and 3, 1. And that happens pretty quickly. But then for 9, there's a value of A for each possible value of B. So we end up with 6 possibilities. And then there's just 1 for 16, 10, and 6. We add those together and we get 10 possible ordered pairs. And some of that's experience. We're always looking for different ways to do casework. And when I can find a way that I can grasp onto where the cases look easy to progress through and there aren't many cases, then I try to grasp onto it that way. Okay, let's take a look at problem number 25. Six students are being grouped into 3 pairs to work on a science lab. How many different combinations of 3 pairs are possible? This is one with multiple solutions, and we're going to talk about at least 2.
Is it possible to have zero people in a group?
Well, it says they're being grouped into 3 pairs.
Oh. Uh, $36.
Fewer than that. One of the things that I like to do with counting problems is to imagine myself as part of the problem, as in I'm one of those 6 students.
I think I overcounted when I got 36.
And I might ask myself, in how many ways I can be paired with a partner?
5 ways.
Yeah. So maybe person A has 5 ways to choose a partner. And then without loss of generality, I'm going to say that's partner B. So now we're going to pair C with a partner. And how many ways can we do that?
You have 3 partners to choose.
That's right. And without loss of generality, let's imagine that's partner D. Now what?
Oh, so there should be 15, right?
Yes.
Oh, you have 5 choices, 3 choices, and then 1 choice.
That's right. And I call this, perspective thinking. Try to insert yourself into the problem and think of it from your perspective, and that can often create, a very practical way to organize the information. But I'm going to talk about another method here too. Let's say that we call these groups, these pairs, pair A, pair B, and pair C. We're naming the pairs, and then we go, well, in how many ways are there for us to put two people in each pair? So what are we counting?
Oh, 6 choose 2. And then 4 choose 2. And then 2 choose 2.
Yeah. That's one way to think of it, is the number of ways to choose 2 of them to be A's, the number of ways to choose 2 of the remaining to be B's, and the number of ways to choose 2 of the remaining to be C's. But this doesn't give us 15. What does it give us?
15 times 6.
It gives us 90.
Yeah.
So is there something wrong?
Probably.
We have 6 times the correct answer.
Yeah. Because when you pick 2 people, you could pick them in different order. Like when you pick the first 2 people and pick the second 2 people, they may be the same groups but switched around.
Right. The naming of the groups was artificial. Sorry. Artificial labels. And so this one that we have here, ABACCB, would be the same thing as BABCCA. That would be the same pairing of the students. We can permute the artificial labels. And when we do, we correct for overcounting by dividing out the total number of permutations of the 3 labels. And that also gives us 15 is the answer. And this is really good because you may run into this. Like, artificial labeling is a really nice modeling technique, right? Whenever we can model something and then work, a problem that we understand more simply, then we've benefited. But there is we have to be careful in understanding how our labels work. And this is not the first time you will see a situation where you can create artificial labels, but that creates a correction that you need to apply to the system, or creates the need to correct the counting method. Okay. Let's do some geometry. Real geometry.
AE and ED is also 3 to 4.
How do you know for sure? I agree, but how do you know?
Because EF is parallel to AB and DC.
Is there some theorem that says if those lines are parallel, then those other segments are in proportion?
Maybe. I just know.
I just know. Now I want you to justify that. This is important. This is good. We found a moment where your instincts are correct, but there is a really, really important mathematical concept behind it. And I don't want you to let that go by, because it's a concept that'll help you with much harder problems. This is the point where you're raising your game from solving like a medium hard AMC level problem to solving an AMY problem.
Do you draw a perpendicular line through A to DC?
Drop in altitude? Is that what you mean?
Yeah.
Maybe.
Similar triangles.
What similar triangles do we have?
AE and the point of AEY to ADX.
I agree.
Since they're proportional, the proportion is 3 to 4.
They?
No, the triangles. AEY to ADX is 3 to 7, but the distance in between is 3 to 4.
I still don't know why. So this is the one, you know, you seem to well, this one right here is the one that you believe is 3 to 7.
Yes.
But we don't know any of these other ratios.
Move the altitude AX over to B.
Ah, good.
And you have another set of similar triangles.
Yes,
so then
we
you can
do.
make sure.
So here's the one that we know is ratio 3 to 7. And then BM to BN is the same thing as AY to AX.
So it's also 3 to 7,
Okay.
which results in 3 to 4.
Okay, I agree with that. How does that help us find EF?
Is it like 7/3 of AB or something?
What does anything have to do with AB?
Divided by 7? Huh.
So we want EF. And what we've done is we've chopped up EF into EY plus YM plus MF. Huh. Do we see EY anywhere? What's another thing that EY is equal to? Look through our ratios. Do you see EY over DX? Do you see that right there? Can you hear me?
Oh, yes.
Okay. Oh, were you on mute?
Yeah.
Okay, got it. So we can rewrite EY as 3/7 DX. Okay. What about YM?
It's just AB.
Yes, which is
7.
7. Okay. And then what about MF?
NC. 3/7 of NC.
Okay.
Oh, and then you put NC and DX together, which is 3. So
Right.
3. 9/7 plus 7, which is 58 out of 7.
That's right.
And that's our answer.
And that is our answer. So having gone through this, so we came up with a pretty good way to go through this. And this was your method. I was thinking of different methods. And I'm going to talk you through them. One of them is going to be intuitive. And this is one where I want you to learn where it is you can and can't trust your intuition, but I want to have good reasons for it when we decide to trust intuition. Now, these two are 7 apart, and these two are 10 apart. And if we were to just kind of drag the dots down from the top and keep them parallel, because the slopes are constant, the amount that the dots are widening out should itself be a constant amount. So it looks like, and it is true, that we have a distance of 7 to 10, and we're going 3/7 of the way across that distance. So 3/7 times 3 added to 7. And that gets us your answer. So that's the quick way to do it, so long as you have a good reason why it's true. Now, there is yet another way to do this, and I don't know if this is going to be good or not. It may be really inefficient. It may be that the way you did this was the best, but I'll show you this because this is actually how we prove that the median of a trapezoid is the arithmetic mean of the bases, or one way to do this. If we were to label these points A, B, C, and D like this, and we have something here, I'll call it X, Y, and we have all lines parallel. And we like parallel lines because parallel lines give us what?
Congruent angles.
Equal angles. And when we have the transversals, we'd like to figure out where it is they cross and form triangles. And so we have that triangle, the red one. We have the green triangle, And then we have the big blue triangle. And all these triangles are similar, and we have, several lengths, and we have several ratios, and we can just start looking for, corresponding ratios within those similar triangles and work until we have what we need. And what we want is X, Y in that case. So I'm going to leave that as one that you can chew on, but I'm going to say, if you want, see if you can use this method to prove that the median, and call this homework, prove that the median of the trapezoid is the average of the bases. The length of the median is the average of the lengths of the bases.
Okay.
Okay, well, it seems like a good stopping point. Thanks for joining me.
Thank you.
You're welcome. See you next
Bye.
time.